Today we're continuing with sequences, mathematical induction, and recursion. Defining sequences recursively. A sequence can be defined in a variety of ways. One informal way is to write the first few terms with the expectation that the general pattern will be obvious. Might say, for instance, consider the sequence 3, 5, 7, and so forth. Misunderstandings can occur when this approach is used, though. The next term of the sequence could be 9 if we mean a sequence of odd integers, or it could be 11 if we mean a sequence of odd prime numbers. So, the second way to define a sequence is to give an explicit formula for its nth term. For example, the sequence A0, 1, A0, A1, A2, etc. can be defined by writing this formula. Okay? The advantage of defining a sequence by such an explicit formula is that each term of the sequence is uniquely determined and can be computed in a fixed finite number of steps by substitution. The third way to define a sequence is to use recursion. This requires both an equation called a recurrence relation, which defines each later term in the sequence by reference to earlier terms, and also one or more initial values for the sequence. Sometimes it is very difficult or impossible to find an explicit formula for a sequence, but it is possible to define the sequence using recursion. Definition. A recurrence relation for a sequence is a formula that relates each term to certain of its predecessors, where I is an integer with k minus I being greater than or equal to 0. If I is a fixed integer, the initial conditions for such a recurrence relation specify the values of the terms. If I depends on k, the initial conditions specify the values for m terms, where m is an integer greater than or equal to 0. So define the sequence C0, C1, C2 recursively as follows. For every integer k greater than or equal to 2. You have the recurrence relation, which is a formula, and then the two initial conditions. You can't say k C0 equals this, because k would be negative numbers. It would refer to numbers outside the sequence. So you have to define the first two elements of the sequence, and then after that, the recurrence relation determines the value of each element based on the previous elements. Find C2, C3, and C4. Feel a sneeze coming on. Anyway, so C2 would be C 2 minus 2 sub 2 minus 1, or C1, or 2, plus 2 times Ck minus 2. C of k minus 2 is 1, so it would be 2 plus 2 times 1 plus 1, so it would be 2 plus 2 plus 1, or 5. And you'd use a similar system for determining C3 and C4 as well. So by substitution, C1 and C2 there, you get C2 equals 5. With C3, substitute C2 for C of k minus 1, and C1 for C sub k minus 2, and you would get 5 plus 3 times 2 plus 1, which would be 31. I'm sorry, no, 5 plus 6 is 11 plus 1 is 12. So there you go. And so on with C4. Let S1, 2, and 3, be, etc., be a sequence that satisfies the following recurrence relation. For every integer k greater than or equal to 1, S sub k equals 3s sub k minus 1 minus 1. Explain why the following statement is true. For every integer k greater than or equal to 0, S sub k plus 1 equals 3s sub k minus 1. Well, in informal language, the recurrence relation says that any term of the sequence equals 3 times the previous term minus 1. Now, for any integer k greater than or equal to 0, the term previous to s sub k plus 1 is s sub k. Thus, for any integer k greater than or equal to 0, s sub k plus 1 equals 3s sub k minus 1. So you can define a recurrence equation relation in multiple ways. Sequences that satisfy the same recurrence relation. Let A sub 1, sub 2, sub 3, etc., and B sub 1, sub 2, sub 3, etc. satisfy this recurrence relation that the kth term equals 3 times the k minus 1 term for every integer k greater than or equal to 2. A sub k equals 3 a sub k minus 1, and b sub k equals 3 b sub k minus 1. But suppose the initial conditions for the sequences are different. Let's look at the first 3 elements following the initial conditions. With A1 equal to 2 and B1 equal to 1, A2 is 6, A sub 3 is 18, A sub 4 is 54. But B starts with 1 in the initial condition, so it would be B sub 2 equals 3, B sub 3 equals 9, B sub 4 equals 27. So it's the same recurrence relation, but different initial conditions lead to different sequences of values. Showing that a sequence given by an explicit formula satisfies a certain recurrence relation. The sequence of Catalan numbers, named after the Belgian mathematician Eugene Catalan, arises in a remarkable variety of different contexts in discrete mathematics. It can be defined as follows for each integer n greater than or equal to 1. C sub n equals 1 over n plus 1 times 2n choose n. Show that the sequence satisfies the recurrence relation C of sub k equals 4k minus 2 over k plus 1 times c sub k minus 1 for every integer greater than or equal to 2. Okay? Well, c sub 1 equals 1 when you multiply it out. C sub 2 equals to 2 when you multiply it out. C sub 3 equals 5. To obtain the kth term and the k minus 1 term of the sequence, just substitute k and k minus 1 in place of n in the explicit formula. And work through the algebra here. Substitute in k plus 1, 2k plus, choose k, and 1 over k plus minus 1 plus 1 over 2 k minus 1, choose k minus 1, which equals 1 over k times 2k minus 1, or minus 2, choose k minus 1. All right? Then start with the right-hand side of the recurrence relation and transform it into the left side for each integer k greater than or equal to 2. So do a lot of multiplication, some factorial math, and multiply it by substitution, and then formula for n choose r, and then rearrange the factors, and then cancel out some factors, rearrange them, and then do some substitution, and then the formula for n choose r again, and then from the definition of C1, C2, C3, make that cancellation, and there you go. Examples of recursively defined sequences. Just kind of a random slide in here. The Towers of Hanoi game problem? That's what they're showing here, but they're going to revisit that a little bit later. It seems out of place. But one of the earliest examples of a recursively defined sequence occurs in the writings of Leonardo da Pisa, commonly known as Fibonacci, who was the greatest European mathematician of the Middle Ages and promoted the use of Hindu-Arabic numerals for calculation. In 1202, Fibonacci posed the following problem. A single pair of rabbits, male and female, is born at the beginning of the year. Assume the following conditions. Rabbit pairs are not fertile during their first month of life, but thereafter give birth to one new male-female pair at the end of every month, and no rabbits die. How many rabbits will there be at the end of the year? One way to solve this problem is to plunge right into the middle of it using recursion. Suppose you know that how many rabbit pairs there were at the end of the previous months. How many will there be at the end of the current month? The crucial observation is that the Number of rabbit pairs born at the end of month K is the same as the number of pairs alive at the month of K minus 2. Because it is exactly the rabbit pairs that were alive at the end of month K minus 2 that were fertile during month K. So, the rabbits born at the end of month K minus 1 were not. Now, the number of rabbit pairs alive at the end of month K equals the number of ones alive at the end of month K minus 1, plus the pairs newly born at the end of the month. Thus, the number of rabbit pairs alive at the end of month K equals the number of rabbit pairs alive at the end of month K minus 1, plus the number of rabbit pairs born at the end of month K, which equals the number of rabbit pairs alive at the end of the month K minus 1, plus the number of rabbit pairs alive at the end of month K minus 2. So for each integer n greater than or equal to 1, let the number of pairs be alive, f sub n be the number of rabbit pairs alive at the end of month n. F sub 0 is the initial number of rabbit pairs, which is 1. Then by substitution into the equation for every integer k greater than or equal to 2, now f sub 0 equals 1, as is already noted, and f sub 1 equals to 1 also because the first pair of rabbits is not fertile until the second month. Hence, the complete specification for the Fibonacci sequence is as follows. For every integer k greater than or equal to 2, f sub k equals f sub k minus 1 plus f sub k minus 2, where f sub 0 and f sub 1 are equal to 1 as the initial conditions. So to answer Fibonacci's question, you calculate f sub 2, f sub 3, and so on through f sub 12. So calculate it all out and get 233 pairs of rabbits, or 466 rabbits in total at the end of the year. When an annual interest rate of I is compounded m times per year, the interest rate paid per period is I over m. For instance, if 3% equals 0.03 annual interest is compounded quarterly, then the interest rate paid per quarter is 0.03 divided by 4, or 0.0075. For each integer k greater than or equal to 1, let p sub k equal the amount on the deposit at the end of the kth period, assuming no additional deposits or withdrawals. Then the interest earned during the kth period equals the amount on the deposit at the end of the k minus 1 period times the interest rate for the period. So the amount on deposit at the end of the kth period, p sub k, equals to the amount of the k minus 1 period plus the interest earned during the kth period. Suppose $10,000 is left on deposit at 3% compounded quarterly. How much will the account be worth at the end of 1 year, assuming no additional deposits or withdrawals? The annual percentage yield, APY, is the percentage increase in the value of the account over a 1-year period. What is the APY for the account? The APR is 3, annual percentage rate is 3%, APY is the actual yield when compounded. For each integer n greater than or equal to 1, let P sub n equal the amount on the deposit after n consecutive quarters, assuming no additional deposits or withdrawals. And let P sub 0 be the initial $10,000. Then by equation 564, with I equals 0.03 and m equals 4, a recurrence relation for the sequence is right here. So the amount on the deposit at the end of the year, 4 quarters, can be found by successive substitution. 10,075, 10,150 and 56 cents, 10,226.69 cents, and then finally 10,303 and 39 cents. Hence, after 1 year, there is $10,303.39 in the account. The annual increase in the value of the account, or the annual percentage yield, is slightly higher than the APR, 3.034%. Recursive definitions of sum and product. Addition and multiplication are called binary operations because only 2 numbers can be added or multiplied at a time. Careful definitions of sums and products of more than 2 numbers use recursion. Given the numbers a, 1, 2, 3 to n, where n is a positive integer, summation from I equals 1 to n of the a sub I, denoted summation 1 to n of a sub I, is defined as follows. With 1 to 1, the summation equals a1, and then recursively, the summation is equal to I to n minus 1 a sub I plus a sub n, where n is, if n is greater than 1. Likewise, the product of with I from 1 to n of a sub I, denoted here, is defined as being the product of I equals 1 to n minus 1 of a sub I times a sub n. And you can see how that just multiplies. You just keep adding terms out to the side until you get rid of the summation symbol. And you get the simple expression. Prove that for any positive integer n, if a sub 1, sub 2, so forth to n, and b sub 1, 2, all the way to n are real numbers, then the summation of from 1 to n of a sub I plus b sub I equals the summation of the from I equals 1 to n for a sub I plus the summation of I sub 1 to n of b sub I. Well, this proof is done by mathematical induction. That's property Pn be the equation here. Show that Pn is true for every integer n greater than or equal to 1 by induction. P sub 1, to be shown first here, is just very simple. When I equals 1 to 1, the summation is just the term in after the summation symbol. So it's just A1 plus B1. And then by definition of summation, that is equal to the sum of the two summations. So hence P1 is true. Now show that for every integer k greater than 1 or equal to 1, if P sub k is true, then P sub k plus 1 is also true. Suppose that k is any integer with k greater than or equal to 1, and that the sequences are real numbers such that this inductive hypothesis and we show that I to k plus 1 is also true for the summations, P of k plus 1. So, now the left side of the equation is this. By definition of the summation, you can write the summation of I to k plus 1 of A sub I plus B sub I is equal to summation of from 1 to k of A sub I plus B sub I plus the A sub k plus 1 plus B sub k plus 1. By the inductive hypothesis, we can make that substitution. And by associative and commutative laws of algebra, make this substitution. And then combine them to make this by the definition of the summation, which equals the right-hand side of the equation. And that's it for that section. And so sequences in recursion continue by solving recurrence relations by iteration. Suppose you have a sequence that satisfies a certain recurrence relation and initial conditions. It is often helpful to know an explicit formula for the sequence, especially if you need to compute terms with very large subscripts or if you need to examine general properties of the sequence. Such an explicit formula is called a solution to the recurrence relation. In this section, we discuss the methods for solving recurrence relations. The method of iteration. The most basic method for finding an explicit formula for a recursively defined sequence is iteration. Iteration works as follows. Given a sequence defined by a recurrence relation and initial conditions, you start from the initial conditions and calculate successive terms of the sequence until you see a pattern developing. At that point, you can guess an explicit formula. Let A sub 1, 2, and 0, 1, 2, and so forth be the sequence defined recursively as follows. For each integer k greater than or equal to 1, A sub k equals A sub k plus 2. A sub k minus 1 plus 2. And A sub 0 equals 1. Use iteration to guess and add an explicit formula for the sequence. In particular, a sub 1 equals a0 plus 2, and a0 is 1, so that's would be a total of 3. A sub 2 is a sub 1 plus 2, which is the 3 that we just calculated, plus 2 would be 5, and so on and so forth. Now we use the initial condition to begin the process of successive substitutions into these equations, not just of numbers, but of numerical expressions. Here's how the process works for the given sequence. Have the initial condition, substitute it into the expression, eliminate the parentheses, keep substituting in until you see a pattern emerge. Since it appears helpful to use the shorthand 2k in place of 2 plus 2 plus 2, etc., k times, we do so starting again from a0. So now, by substitution, have the initial condition, and it's 1, and then 1 plus 2 times 1, and then substitute in. At this point, it seems likely that the general pattern is 1 plus 2n. So that would be the answer. It's only a guess after all. Okay. So a sequence like the one in which each term is equal to the previous term plus a fixed constant is called an arithmetic sequence. A sequence is called an arithmetic sequence if and only if there is a constant d such that a sub k equals a sub k minus 1 plus d for each integer k greater than or equal to 1. It follows that a sub n equals a0 plus dn for every integer n greater than or equal to 0. Another arithmetic sequence. Under the force of gravity, an object falling in a vacuum falls at about 9.8 meters per second, faster each second than it fell the second before. Thus, neglecting air resistance, a skydiver's speed upon leaving an airplane is approximately 9.8 meters per second 1 second after departure, and 19.6 meters per second 2 seconds after departure, and so forth. If air resistance is neglected, how fast would the skydiver be falling 60 seconds after leaving the airplane? Let S sub n be the skydiver's speed in meters per second, n seconds after exiting the airplane. Assuming there's no air resistance, then S sub 0 is the initial speed, and since the diver would travel 9.8 meters per second faster each second after than the second before, S sub k equals S sub k minus 1 plus 9.8 meters per second for every integer k greater than or equal to 1. It follows that S sub 0, 1, 2, and 3, etc. is an arithmetic sequence with a fixed constant of 9.8. And thus, S sub n equals S sub 0 plus 9.8 n for every integer n greater than or equal to 0. Hence, 60 seconds after exiting and neglecting air resistance, the skydiver would travel at a speed of 588 meters per second. Of course, that's over half a kilometer per second, or over a third of a mile per second, which is very fast for a human being to travel. But there's air resistance to take into account, and terminal velocity and all that sort of thing reduces the speed at which the skydiver is falling considerably. Now, the explicit formula for a geometric sequence. Let R be a fixed non-zero constant, and suppose a sequence A sub 0, 1, 2, and 3, etc. is defined recursively as follows. A sub k equals R times A sub k minus 1 for each integer greater than or equal to 1. And A sub 0 equals A. Use iteration to guess an explicit formula for the sequence. By substitution, you see a pattern emerging here. So the guess is that A sub n equals R to the n times A, or A times R to the n for every integer greater than or equal to 0. A sequence is called a geometric sequence if and only if there is a constant R such that A sub k equals R times A sub k minus 1 for each integer greater than or equal to 1. And it follows that A sub n equals A0 times R to the nth power. As shown in example 567, if a bank pays interest at a rate of 4% per year, compounded annually, and A sub n denotes the amount in the account at the end of the year n, then A sub k equals 1.04 times A sub k minus 1 for each integer greater than or equal to 1, assuming no deposits or withdrawals during the year. Suppose the initial amount deposited is $100,000. Wish somebody would put that in my savings account. And assume that no additional deposits or withdrawals are made. How much will the account be worth at the end of 21 years? And in how many years will the account be worth $1 million? Well, A sub 1, sub 2, sub 3, etc. is a geometric sequence with the initial value of 100,000 and a constant multiplier of 1.04. Hence, A sub n equals 100,000 times 1.04 to the nth power for every integer greater than or equal to 0. After 21 years, the amount in the account would be 100,000 times 1.04 times 10 to the, or 1.04 to the 21st power, approximately equal to $227,876.81. This is the same answer as that obtained in example 567, but is computed much more easily, at least if a calculator has a powering key. If the calculator with a powering key is used. Let the number t be the number of years needed for the account to grow to 1 million. Then you would calculate 1 million equals 100,000 times 1.04 to the t power. Dividing both sides by 100,000 equals 10 equals 1.04 to the t. And taking the natural logarithm of both sides results in natural log 10 equals natural log 1.04 to the t, and a little algebraic magic, log 10 equals t times log 1.04, so t equals log 10 over log 1.04, which equals 58.7. So the account would grow to $1 million in approximately 58.7 years. Start saving now, while you're young. This box indicates some quantities that are approximately equal to certain powers of 10. Just kind of some trivia. 10 to the 7th is the number of seconds in a year. This one's a little bit inaccurate, but 10 to the 9th is the number of bits or bytes of memory in a gigabyte computer. This is a little old. They're usually larger than that now. 10 to the 11th is the number of neurons in a human brain, give or take. 10 to the 17th, the age of the universe in seconds, according to one theory. 10 to the 31st, number of seconds to process all possible positions of a checkers game if moves are processed at a rate of 1 per nanosecond. And 10 to the 81st is the number of atoms in the universe. And 10 to the 111th, number of seconds to process all possible positions of a chess game if moves are processed at a rate of 1 per nanosecond. So get to some pretty big numbers pretty darn quick. Using formulas to simplify solutions obtained by iteration. Recall that the towers of a Hanoi sequence, M1, M2, M3, satisfies the recurrence relation m sub k equals 2m sub k minus 1 for every integer k greater than 2. For those that don't know, the Towers of Hanoi is a little game that you transfer disks from one point to another, and the number of moves it takes is determined by how many disks are being used, and that is shown with the 2 times m sub k1 minus 1 for the number of moves with k number of disks. And the initial condition is m1 equals 1, because it just takes one move to move one disk from one point to another on the board. Use iteration to guess an explicit formula for this sequence. Make use of a formula for the sum of a geometric sequence to simplify the answer. By iteration, you see and that substitution, and then substitution, then substitution, then substitution. So you get for m sub 5 is 2 to the 4th plus 2 to the 3rd plus 2 to the 2nd plus 2 to the 1st plus 2 to the 0th. So these calculations show that each term up to m sub 5 is a sum of successive powers of 2, starting with 2 to the 0th power equals 1, and going up to 2 to the k, where k is 1 less than the subscript of the term. The pattern would seem to continue to higher terms because each term is obtained from the preceding one by multiplying by 2 and adding 1. Multiplying by 2 raises the exponent of each component of the sum by 1, and adding 1 adds back the one that was lost when the previous one was multiplied by 2. For example, n equals 6. M sub 6 equals 2 to the 5th, plus 2 to the 4th, plus 2 to the 3rd, plus 2 to the 2nd, plus 2 to the 1st, plus 2 to the 0th. So, it seems natural that, in general, this is true. And the formula for the sum of the geometric sequence would be this here, and the explicit formula would seem to be m sub n equals 2 to the n minus 1. Checking the correctness of a formula by mathematical induction. As you can see from some of the previous examples, the process of solving a recurrence relation by iteration can involve complicated calculations. It is all too easy to make a mistake and come up with the wrong formula. That is why it is important to confirm. Oh, excuse me. That is why it is important to confirm your calculations by checking the correctness of your formula. The most common way to do this is to use mathematical induction. We have obtained a formula for the Tower of Hanoi sequence. Use mathematical induction to show that this formula is correct. What does it mean to show the correctness of a formula for a recursively defined sequence? Given a sequence of numbers that satisfies a certain recurrence relation and the initial condition, the job is to show that each term of the sequence satisfies the proposed explicit formula. In this case, you need to prove the following statement. If the sequence is defined by m sub k equals 2 times m sub k minus 1 plus 1 for each integer k greater than or equal to 2, and m sub 1 equals 1, then show that m sub n equals 2 to the n minus 1 for every integer n greater than or equal to 1. Proof of correctness. Let m1, 2, 3, etc. be the sequence defined by specifying m1 equals 1, and mk equals 2m sub k minus 1, plus 1 for each integer k greater than or equal to 2. And let the property p sub n be the equation m sub n equals 2 to the n minus 1. We will use mathematical induction to prove that for every integer n greater than or equal to 1, p sub n is true. So, show that p sub 1 is true. Show that m sub 1 equals 2 to the 1 minus 1. Well, that means m sub 1 by definition is m sub 1 is equal to 1. And the right-hand side of p sub 1 is 2 to the first minus 1, or 2 minus 1, which is 1. Thus, the two sides of p sub 1 are p of 1 is equal to the same quantity, and hence p of 1 is true. Now show that for every integer k greater than or equal to 1, if p of k is true, then p of k plus 1 is also true. Suppose that k is any integer with k greater than or equal to 1, such that the inductive hypothesis is m sub k equals 2 to the k minus 1. Must show that m sub k plus 1 equals 2 to the k plus 1 minus 1. All right. But the left-hand side of P of k plus 1 is 2m sub k plus 1 minus 1 plus 1, or 2m sub k plus 1. Now substitute in the inductive hypothesis, which defines m sub k, and you get this equation here. It's a distributive law, in fact, in the fact that 2 times 2 to the k equals 2 to the k plus 1. And basic algebra gives you this equation here, which equals the right-hand side of P of k plus 1. And since the basis and inductive steps have been proved, it follows that by mathematical induction that the given formula holds true for every integer n greater than or equal to 1. Discovering that an explicit formula is incorrect. Things don't always go as planned. Let C sub 0, 1, and 2 be the sequence defined as follows. C of k sub k equals 2c sub k minus 1 plus k for each integer k greater than or equal to 1. And C sub 0 equals 1. Suppose your calculation suggests that the sequence satisfies the following explicit formula. C sub n equals 2 to the n plus n for every integer n greater than or equal to 0. Is the formula correct? Well, start to prove the statement by mathematical induction and see what develops. The proposed formula satisfies the basis step of the inductive proof, since on the one hand, C sub 0 equals 1 by definition, and on the other hand, 2 to the 0th power plus 0 equals 1 plus 0 equals 1. So in the inductive step, you suppose that k is any integer with k greater than or equal to 0, such that C sub k equals 2 to the k plus k. And then you must show that C sub k plus 1 equals 2 to the k plus 1 plus k plus 1. To do this, you start with C sub k plus 1, substitute from the recurrence relation and use the inductive hypothesis, and you get, with basic algebra, this expression here. To finish the verification, therefore, you need to show that 2 to the k plus 1 plus 3k plus 1 equals 2 to the k plus 1 plus k plus 1. Well, some simple addition and, well, subtraction. This equation is equivalent to 2k equals 0, which is equivalent to k equals 0. But this is false, since k may be any non-negative integer. For instance, when k equals 1, k plus 1 equals 2, and the two expressions do not hold true to themselves. Of course, you could have also substituted in different values for k and shown by counterexample that the equation was in fact false. So the formula does not give the correct value for C2, hence the sequence does not satisfy the proposed formula. I believe that is it. Anything, any kind of questions that you might have? I guess not. Well, have a wonderful day. See you on Thursday. Next Tuesday, there will be a quiz on Chapter 5. Open notes as usual. So have a good day and see you next time.